All right, let's begin today's stream, and let's see this. Hey, hi, bro. What's up? Oh, even I don't know how to be good at bit manipulation. Like my bit manipulation is not that good. That's why I'm continuing doing bit manipulation today. So what we can maybe do is do some lead code together today in today's session, because I'll be most probably solving at least 3 questions from this. So we can solve it side by side together. I'll keep on writing down my thought process or my approach, and you can continue with your approach. And if you see I'm doing any mistake over here, then you can also start writing it in chat, right? Okay, this is the wrong step that I took, or anything like that, because even I'm here to improve my bit manipulation skills today. As far as I know, bit manipulation just works there are just 3 to 4 operations, right? Is OR operation, AND operation, OR operation, and left shift, right shift. Like these are the main operations that work in bit manipulation, I think. So let's see if we can get a hold of it or not. Given a positive integer and write a function that will number of subjects. Okay, all right. First of all, let's do the usual stuff with Obsidian. Oh, wait a second. Why do I have this? I can close this for now. No worries, bro. Take care. No worries. Take care. Take proper rest. What are the companies? Okay, let's see. Let's see the topics. All right, and write a function that returns number of set bits in its binary representation, also known as Hamming weight. Okay, set bits is basically number of bits which are just 1, right? Oh, I think it's pretty easy, right? Like all I have to do is I'll just revise. Okay, left shift is this, right shift is this. Cool, awesome. And let's see. right shift right. Will this work? Is this how you do left shift right shift? Yeah, I think this is what the fuck. First type is int, second type is boolean, it is saying. Okay. Got accepted. This is the base scenario, right? Like it is just a brute force approach over here. How can we optimize this? That's the question, right? For example, this is 1011. What do you do? This 11. It is 2, right? So basically, if 128 has it, yeah, it is 1. It represents 1, correct? So what we can do, what this happened, let's go right books. So it's like, all right, how do I, what I mean by this is, (128) in bits is this. Actually, all right, let's do it. (125) would have bit 1. Yep, there we go. 11 is 1011, right? What is 10? 10 becomes what? 1, 2, 4, 8 becomes 1010. That's how 10 is represented. 9 becomes what? 8 and 1. So it becomes 1001. That's how it works. So there's a pattern over here that first bit will always be on alternate numbers. Basically, for 1 it is 1, then for 2 it will be 0, and for 3 it will be 1 again. Can this this is one of the observations, right? Now how do we do that? Let's see. Let's do it for 11 actually. So actually let me start from, let's say, 1. 1 becomes what? 0. Okay, how many bits do I need to write? Till 11 it is what? 4 bits. Yeah. That's how it works, right? These are the number of bits from 1 to 11. Now, can we somehow create a shortcut or an optimized solution rather than visiting every single bit of this number? What is 12 over here? 12 becomes what? $15. That's how the number of bits get covered, right? Given not 3 bits. This is 128, right? 128, then I go to 64. What is 32? 16 bits is what? This is 16 bits. Then you go to 8, 8 is 100, 4, 4 is 100, 2. You go to 2, 2 is 10. You reach to a conclusion that okay, that's how I get number of set bits. Alright. If I check for 11's case, it is 1011. Divided by 2 becomes 5001. With 3. Oh. Does this hunch work? But technically that's what I'm doing, right? I'm moving it ahead, then I'm moving it ahead. I'm moving it ahead. That's what I'm doing. I'm basically dividing it by 2 and everything. This is the same thing. This is not the correct way of optimizing it. Of course, it's doing it with the Gaussian, but it's the same thing. I need to see the optimal solution. Like, what are they saying? How would you optimize it? Like, it is already running in O of 1, like O of 1 time complexity and space complexity, right?
Hey everyone, welcome back and more Leetcode today. So today let's solve number of 1 bits. This is actually another blind 75 problem, and we've been tracking all blind 75 problems on this spreadsheet. The link to that will be in the description. Today we'll be doing in an unsigned integer, which isn't really important for this problem because all we want to do is count the number of 1 bits that it has. So the concept is pretty simple. So when you take a look at this number, we can see it's made up of zeros and ones, and we just want to count how many ones it has. Clearly it has 1, 2, 3, so we can return 3. But how can we actually count the bits? So obviously we need to do a little bit of bit manipulation. I'm going to be showing you 2 different solutions. One of the solutions, the second one, is going to be slightly faster if you're interested in it, and it's pretty difficult to come up with. But the first solution is a little bit more straightforward and is more doable. So like I said, the easiest way is just to count manually bit by bit, and then see which one of them are ones, and then increment our total, and then return the total. But let's see how we can actually accomplish that. So how do we know? Let's say we want to look at the first bit on the right side. How do we know if it's a 1 or a 0? Well, there's actually 2 different ways. One way is you can AND it with the integer 1. So since the integer 1 just has 1 here and then the rest of them are zeros, when we do a logic AND operation, logic AND is basically taking the AND of every bit, but we know that every bit is going to be 0 when we take the logic AND. It's going to be 0 for every bit except for this one, which can either be 0 or 1. It'll be 1 if the bit in the input integer is 1, then we'll get a 1 in the output. If it's a 0 over here, then we'll get a 0 in the output. So that can tell us if there's a 1 here or a 0 here. Another way to do it is just to mod this by 2. Modding is basically taking this, dividing it by 2, and getting the remainder. Since this is a 1's place, if we mod it by 2 and there is a 1 here, we'll get a 1 in the output. If there's a 0 here, we'll get a 0 in the output. So we have 2 different ways to do it. I think I'm going to stick with modding, but you can do it either way. Okay, so we have a way to detect if the first bit is a 1 or a 0. But what if we want to look at the next bit and the next bit and the next bit? How do we do that? Well, the easiest way would just be to take all the rest of the bits and then shift them to the right by 1. And luckily, most languages can natively support this, and it's a very efficient CPU operation. This is kind of the preferred way to usually do it in bit manipulation, just shift every bit to the right by 1. We can achieve basically the exact same thing by taking this and then integer division by 2. Dividing it by 2 will basically shift all the bits to the right by 1 as well. But usually the bit shift operation is a little bit more efficient on your CPU, so that's what I'm going to prefer. So basically we're going to take these, shift them to the right. So now we're going to have a new integer 1, 0, 1. Again, we want to know if this bit is 1 or 0. We're going to mod it by 2. We're going to get another 1. So far we have counted two ones. And again, we would want to take these, shift them to the right. This time we get a 1, 0. We mod this by 2. We get a 0 in the output. That means there's a 0 here, so we don't add to our total this time. And lastly, we take this, shift it by 1. We get another, we basically get the integer 1. We mod it by 2. 1 divided by 2, the remainder after that is just 1. So we got our third 1. So our total so far is 3 ones that we counted. And lastly, we're going to take this and then shift it to the right. But what exactly is going to be remaining after we do that? Well, basically 0. And once we have a 0, it basically means we have all zeros, right? 32-bit integer will have 32 zeros. And that basically means that we can stop our algorithm now. And we're done. So we counted in total 3 ones, and that's what we can return. So once you're familiar with these bit operations, it's a pretty straightforward problem. So let's code up the first solution. Okay, so now let's code it up. I'm going to declare one variable for the result, which is basically the total count, the total number of ones that we're going to have, and I'm going to continue.
I want to see second solution. Yeah, that's what I
that
want.
while loop we had is going to run 32 times. So really the time complexity is big O of 32, which is constant time, right? No matter what the input is, the time complexity is not going to scale up. So basically the time complexity is constant. We can say it's big O of 1. And there's no real extra memory complexity needed as well. So it's also big O of 1. But a small downside of our solution is it has to count, it has to look at every bit, even the ones that aren't ones. So for example, what if we had a number like this? In this case, we're going to look at this bit first. Okay, it's a 1. We're done with that. Then we're going to look at this bit, this bit, this bit, this bit, every bit here, even though they're zeros, right? That kind of wastes time. Wouldn't it be convenient if we only had to look at the bits that were 1? That meaning our algorithm only has to run as many times as how many ones are actually in the input. And yes, there actually is a way we can do this, but it's not very easy to come up with. And it's probably not even worth coming up with because the time complexity will be the same. It'll still be constant time and constant space. But it might be good to just, get really good at your bit manipulation tricks and stuff. And maybe you'll see this in an interview. So the main operation we're going to be doing in our while loop with this trick is basically taking n and setting it equal to n logic anded with n minus 1. And this is what we're going to do in every iteration of a loop. And each time we do that, we're going to increment our result by 1. But the question is, why does this work? First, let's see what will happen. So what's going to happen? Let's take this integer and subtract 1 from it, right? That's what we're going to do over here. So n minus 1, which is going to be this. And now we're going to logic and them together. What are we going to get when we do that? We're basically going to be removing this, right? We're going to get n minus 1 itself. And we're also going to increment our result by 1 now, regardless of what the output happens to be. Okay, so now our n value is going to be set to this. Okay, so now our new value is going to be 100. And all zeros. Okay, now we're going to take this number and subtract 1 from it. What is that going to look like in binary? Well, it's going to be 0, 1, 1, 1, 1, 1, 1, 1. Okay, and now we are going to logic and these two together. What's that going to look like? Well, we're logic anding every bit. This one is going to turn into 0 now. And the rest of these are also going to be 0. Even though we have ones in the bottom number, we have all zeros in the number above. So now we're actually done with our entire loop. Now we have all zeros. We incremented our result by 2. So now our result is 2, and then we return, right? Which makes sense because when you look at the original number we started with, yes, it did have 2 ones in it. But how did this algorithm work? Well, it's actually really simple, but it's definitely not easy to come up with. What we're doing when we're subtracting 1 from itself is we're basically getting rid of a bit, right? When we took this number and subtracted 1 from it, we got rid of this 1 bit, right? And remember, we're counting 1 bits. So when we did that, we increment our result by 1. But then why did we logic and it together with itself? Well, basically, since the rest of the numbers stayed the same, and we took this 1 away here, and then we logic and them together, we're basically removing that 1 bit. So then when we logic anded these two together, you can see that the 1 bit was removed, but the rest of the number stayed the exact same on the left. Okay, that works. But what about this number, right? Then we were left with this, and then we subtracted 1 from it. Then what did we do? Well, again, when we subtracted 1 from it, we basically got rid of the next 1 bit, right? You can see that when we subtracted 1 from it, this is what the number looked like. We got rid of this 1 bit, but we introduced a bunch of other 1 bits. But these are all okay because we know they're going to be, and any 1 bits that we introduce are going to be on the right side. And we know that if we just deleted this one, it was the rightmost 1 bit that we had. So any ones that are introduced to the right side won't matter in this number. This is n minus 1, by the way. Any ones here won't matter because remember, every time we do that, we're logic anding them together. We're logic anding n with n minus 1. So these are all going to cancel out, and this is going to cancel out as well, the position where we remove the 1 bit. So basically what we're doing here is we're skipping all the zeros in between. We're basically allowing ourselves to run the loop as many times as basically as many 1 bits exist in the input integer. It's kind of a really weird trick, but it definitely works, and it makes sense why it works. Now we can code it up, and it's pretty simple. So you can see that this was our original solution, and we only have to modify this a little bit. So
Whoa, that was pretty insane actually. I'm using Obsidian. Oh, my bad. Give an integer n. Return an array answer of length n plus 1 for such that for each I, answer of I is the number of ones in the binary representation of I. Alright. It's like you check number of set bits in every single number. Right. So it's like doing the same thing, just that we did. And that would give us the whole answer. Like most probably that should be the answer which I just did, right? And it would give me the whole thing. So it's like, wait a second, I'll just quickly make the notes. Oh, that's asking pretty much a lot of companies actually. Okay, cool. We have to do it from 0 to n or 1 to n. 0 to n, right? So it would look something like yeah, it works. Is there any better approach to solve this?
Hey everyone, welcome back, and let's write some more neat code today.
Let's confirm if my answer is correct. I don't need inbuilt functions. And its code is completely different actually. Let's see.
So today we're going to be solving a binary question, counting bits, and this is one of the binary questions from the blind 75 list that we've been tracking in the spreadsheet, so we will finally be adding a video solution to this binary problem. I'm pretty sure it used to be a medium problem, which is why it's highlighted yellow, but I think it got changed to an easy problem. So the statement is pretty simple. We're given an integer n, and we want to return an answer array of length n plus 1, basically a value for every integer in the range from 0 all the way up until n. So if n happened to be 0, then we would just return a single integer. If 0 happened to be 2, then we would return 3 integers for 0, 1, and 2. And basically, for every value in this range, 0 to n, so if n was 2, we would have 3 values in that range, 0, 1, 2. For each of these values, we want to know what is the number of ones in the binary representation of this particular integer. Now, what's the binary representation of 0? It's of course just 0, right? You could add multiple zeros, but it's still going to be 0. What's the binary representation of 1? It's going to be just 1, right? You can have some leading zeros. We have as many as we want, but at the end, it's just going to end with a single 1. So there's only one occurrence of the integer 1 in the binary representation of 0. So far, our output is going to be representation of 2. The binary representation of 2 is going to look like this, 1, 0. You can have some leading zeros, but this is the main part that we're looking at. So it just has a single 1. So then the output is going to be 1 for that. So the array that we would return is going to look something like this, 0, 1, 1. Now, the brute force way to solve this problem is going to be n log n, and that solution is going to look something like this. Let's say we had an arbitrary value such as 2 or maybe even 3, right? We know the binary representation of 3 is going to look like 1, 1, right? So how are we going to count the number of ones in the binary representation of 3? Well, first let's get the ones place, right? Is this going to be a 1 or a 0? How can we get that? Well, we can take 3, mod it by 2, which is going to give us 1. So we have at least 1, 1 here, right? So we already looked at this position. So what we do is basically cross it out, and then we just want to look at the remaining portions. Now, how can we actually do this? Like what kind of operation can we do? Basically, if you take 3 and divide it by 2, integer division here, and most programming languages will do this basically by integer division. What that's going to do to this integer is it's basically going to take that ones place and remove it, take the remaining bits, and then shift it to the right. So it basically does exactly what you would want to do. And of course, what do we get when we take 3 and divide it by 2? Integer division is going to give us a 1. So we're basically going to get this, and when you look at that, yes, this is the binary representation of 1, right? So now we're going to take this and mod it by 2 as well. We're taking 1, modding it by 2. That's also going to be a 1. So far we've counted 2 different ones for this integer, and again, we're going to take this this ones place now and chop it off, and now we're left with a single 0. So if you take 1 divided by 2, yes, you get 0. Once we get to 0, that's how you know when we're stopping, right? There's obviously in 0, there's no more ones in 0. So basically we counted 2 different ones. So that's how we would do it for every particular integer. The example I showed right now is 3, and to get this, the time complexity is log n, because for any integer n, how many times can you divide it by 2? Well, of course, that's just log base 2n. Now, we don't really worry too much about the base usually, but yes, it's going to be log n, log base 2n. That's how many times we could divide any particular integer n by 2. And of course, we know we're doing this for a bunch of integers in the range all the way from 0 to n. So we're doing this n times. Doing a log n operation n times is going to be time complexity n log n. Now, there's some repeated work that we can eliminate that you can easily recognize when you actually draw out the bit mappings, the binary representations of a bunch of integers. And with that repeated work, we can actually get a working O of n solution. Let me show you that right now. Now, I just drew out the binary representations from 0 all the way up to 8. So we know that, of course, 0 has 0 ones in the binary representation. When you get to 1, we have 1 occurrence of 1 in its binary representation. For 2, we have 1. For 3, by looking at this, we can see we have 2 different ones. And now when you get to 4, you really start to notice how we are doing this repeated work. Notice how for 4 all the way to 7, we have a 1 1 in this place, right? In the most significant place, we have a 1. And notice how the remaining portion of this, and then this, and then this, and this, these 4 are just repeats of the previous 4 that we calculated, right? Because we're counting 0, 0, adding a 1, right, to 4. When you add a 1, you just change it to this. From 4, when we add a 2, we get this, which is basically the binary representation of 2 itself, right? And then you get a 1, 0, and then you get a 1, 1, which is matching over here. So now looking at it, this is the binary representation of 4, right? There's just a single 1 in this position. So if we wanted to take 0 and add 4 to it, we would just take this position and add a 1 here, right? That will take us 4 positions ahead. And if you had a 1 and you change this bit to a 1, we're adding 4 to it. So you can take a 1 and change it to a 5 by taking that bit. So similarly, when we get to 4, we know that yes, we're going to have one extra 1 in this position, right? Because we just got this one. This one represents a 4. This is the most significant bit so far. But for the remaining ones, all we have to do is take this, offset it by 4, and get here and count how many ones were over here. So when we're calculating how many ones for 4, we're just saying it's 1 plus the number of bits at position 0. How many ones were in position 0? That's our DP. So you can see this is a dynamic programming problem because we're using the previous results that we calculated to compute the new results. In other words, this is going to be 1 plus DP of n minus 4. And actually, when you look...
That's what we are also doing. So makes sense, actually. All right. Cool. Reverse bits basically change. What do you want by reverse bits? All right. Reverse bits, got it. Let's take a smaller example actually over here. Right. So delete all this. Reverse bits becomes okay. Let me just call that and remove this. Reverse bits. How does that work? Let's do it on a smaller example actually. So for example, it is, let's say we do it for 11. It becomes what? 1101, correct? Which is ideally 13, right? So let me do one thing. I'll add a case over here, which is 1011, right? Let me run it and check for 11 now. What? Oh, Right, and this. Oh, got it. So got it. Return 13. If I do a return 13 over here, does it work? Okay, it would become something like this then. Got it. So it's like this, and we need whole 32 bits. Got it. How do we do it? Let's see. Okay. How do we do this? Do you see any pattern over here? Like, I think we can do it this way now. We create a rise and do a right shift from here and do a left shift to here. So it would work, right? Process time limit exceeded. Wow. Why did it not work? Oh, it was never one in and one. Okay, let me do this. What start? I didn't get your message, bro. What do you mean by start over here? Just give me the answer, right? Right. This is the case. What it does is raises 0. In or please speak Hindi. Oh, I'm actually being bilingual. I think that should work. But okay, doesn't English suit you, bro? I think if you're in tech, English must be your language, right? Let me know where you are having problem with English. I'll try to explain it in Hindi. No worries. Okay, what's the issue over here? What's happening? Let's see. Okay, the system good. Right. Yeah, teacher.do binary string, cool. Yeah, it should give me 101. This is what it should give, right? Why is this giving me the 0 over here? Right, what if I do it with 1? This would give me definitely 0 answer, right? So what's the issue over here? No. Let's do a dry run on this actually. It is what? First step gives me this, and other thing becomes this. Next step gives me what you take its and with. What's the issue exact issue over here? Yeah, it should work fine. What's the issue? Like, what's happening over here? Oh, wait a second. Is this the issue? I need to traverse 32 times now. This has to be 32 over here. And alright, what are we supposed to do? I have 0 over here. Cool. I need 32 bits. Right. Oh, the only thing is it's doing the left shift beforehand. But why? What? Okay, give me a moment because I'll be over here. This. I don't get it. Like, what's the issue with my code? I don't understand that. Awesome. Works like a charm. I think that's enough. The solution is enough. All right, that's it for today. Let's do rest of the questions tomorrow, and we can be done with this sheet tomorrow, I guess. So yeah, that's it for today. Thanks for watching. Have a good night. Bye bye.